Welcome back to Honors Calculus. In this video, I'm going to be introducing you to several of the integration rules. Last time, we saw that we could use a guess and check approach in order to evaluate integrals, and it certainly works, but it would be nice if we had something a little bit more streamlined. So in this video, I'm going to go through some of the rules we have for differentiation and see if we can find an integration equivalent to them. Without further ado, let me get my head out of the way and let's dive into that. The rule that we most commonly use in differentiation has been the power rule. The derivative of x to the n power is n times x to the n minus 1 power. And as we've guessed and checked on indefinite integrals, we saw that this worked pretty well the same way. If we want to take the integral of x to the m power, we saw that, well, multiplication didn't quite do the job. We ended up having to do some dividing instead. The integral of x to the m power is 1 over m plus 1 times x to the m plus 1 plus our arbitrary constant of integration. And we can see that this works using a guess and check approach. If I want to, for example, evaluate the integral of x to the 7th, following our new power rule for integrals, it looks like this is going to be 1 over 7 plus 1, which is 1 over 8, times x to the 7 plus 1, which is 8, plus our constant of integration. And if you try to take the derivative of 1/8 times x to the 8 is, well, 1/8 times 8 is 1, x to the 8 minus 1 is 7. So the derivative of 1/8 x to the 8th is x to the 7th. You can use guess and check to verify that it works. We also have the property of linearity, which we've already discussed for integrals. The integral of a times f of x plus b times g of x is equal to a times the integral of f of x plus, I need some dx's in there, sorry about that. Let's get the whole thing down. Dx is equal to a times the integral of f of x plus b times the integral of g of x. All right, we've used linearity already when we've talked about integrals, so it's nothing new. But combining that with the power rule allows us to take care of integrals of many powers of x. So we can take the integral of, say, 3x squared plus 4x plus 5, and we can split that up as 3 times the integral of x squared plus 4 times the integral of x plus 5 times the integral of dx. And then using the power rule, x squared is a power, m equals 2. So our coefficient in front stays our coefficient in front. We get 1 over 2 plus 1, which is 3, times x to the 2 plus 1, which is 3 power. We get 4. X is x to the first power, m is 1. So this is 1 over 1 plus 1, which is 2, times x to the 1 plus 1, which is 2. Then we get 5. Now, dx, there's no x there at all. But here I'm going to use the rule from algebra. X to the 0 power is equal to 1. So we have here m is equal to 0. We get 1 over 0 plus 1, which is 1, times x to the 0 plus 1, which is 1 power. And then we have to make sure to remember to add our arbitrary constant because we have a family of solutions that all work. Simplify this expression. We get 3 times 1/3 is 1, so that's x cubed. 4 times 1/2 is 2x squared. 5 times 1 over 1 is 5x plus c. We can also use this do power rule to deal with things that involve square roots. So for example, the integral of the square root of x dx is, well, square root of x is x to the 1/2 power. So m is 1/2. 1/2 plus 1 is 3/2. And 1 over 3/2 is 2/3. And once again, you can use the derivative to check. The derivative of 2/3 x to the 3/2 will be 2/3 times 3/2, those will cancel each other out, times x to the 3/2 minus 1, which is 1/2. So you can use that to check. There is one thing that we have to be careful about, though. The integral dx over x. Well, 1 over x is x to the negative first. So using the power rule, we have that m is -1. So we have 1 over -1 plus 1, which is 0. All right, that's a problem, right? 1 over 0 times x to the 0 is 1 divided by 0, which is undefined. We definitely don't want an undefined solution. So we don't have the tool right now for dealing with x to the -1. Our power rule for integrals is fundamentally flawed. It will work for literally any other power, but the power rule for integrals only works when m is not equal to -1. That's so important, I'm going to scroll back up to where I wrote the power rule. And put that caveat in. Our power rule says that x to the m is 1 over m times x to the, or 1 over m plus 1 times x to the m plus 1 plus c whenever m is not -1. When m is -1, we need a completely different rule, and it's going to be a couple of videos before I get there. It's actually going to be in the second semester of calculus that we see how to deal with that one corner case. But that takes care of powers. With linearity, that takes care of polynomials, that takes care of square roots, and that takes care of some reciprocals, some division, not a lot. We'll try to build up more a little bit later on. For right now, I'm just going to look a little bit at trig, not THG, trig. And we have a couple of rules of differentiation. The first two translate very nicely. If the derivative of sine is cosine, that means that the integral of cosine is sine. And if the derivative of cosine is sine, that means that the integral of sine is the negative of cosine. Careful here. In derivatives, sine stays positive, cosine goes negative. In integrals, cosine stays positive, sine switches to negative. That's just something you need to know. But it is a pattern and it is something you can remember. The other two integrals I can write down. They're a little bit less obvious. They're going to be a little bit less useful, but the integral of secant squared x is in fact tangent, and the integral of secant times tangent is in fact secant. All right, they're not quite so nice. It's not the integral of tangent or the integral of secant, but it gives us something to work with at least. Once again, some things to look forward to in future videos in the second semester of calculus: how to deal with the integral of secant on its own, how to deal with the integral of tangent on its own. All right, but with all of that out of the way, and thinking about the tools we've been building up, I would like you to try to come up with the integral of x plus the sine of x dx. See where you can get to on that one, and I'll see you in the next video.